All right, thanks everyone. So we're going to get started with the next session, and our first speaker is Davide Crapis from the Ethereum Foundation.
Hi everyone, I'll talk about this Endgame EIP-1559, which is actually two EIPs. So I start with like the current state of resource pricing on Ethereum L1. Then I'll introduce something we call multidimensional metering. And then finally, I'll discuss this full multidimensional pricing with a few options we have in EIPs being drafted. Yeah, so the TLDR is that the current resource pricing on L1 is quite inefficient. So we have a naive price controller that does like some simple demand estimation block to block, like very naive. And then the individual resources that the EVM consumes, like compute, state access, state growth, memory, they're not even being metered. So there is no simple way of pricing multiple resources. And over the years, many solutions have been proposed, but then like the range is like from too academic and hard to implement. There was like a stream of papers on multidimensional fees, including like some of my own work with co-authors. Then like some were like too simple and inefficient. And also Vitalik had a couple of posts on things that are implementable in the EVM, but kind of like a UX nightmare. So yeah, we have some recent breakthrough here, so that's why I'm excited to like talk to this audience, because definitely relevant to MEV. And yeah, so basically the two steps are like, first we improve metering, and then we can unify pricing. Yeah, so in Ethereum there is like multiple resources, but we have one single price. And this is because like in effect, like the virtual machine tracks only one resource. Like all the resources are mapped to this common currency called gas that like most people that work on it know. And then basically the protocol only specifies conversion rates from like opcodes and different resources to this single one. And then the protocol today is metering this gas consumed by transaction, which is effectively used for two purposes. One is like controlling like that the block resource usage is within some admissible limit. And then the second one is like charging transactions for what they consume, and then manage congestion. Yeah, so the problem of resource management, basically like, why is this inefficient? So the properties we want is that we want to be within a safety limit for each block, but also we want to be efficient in the sense that we would like to utilize like most of the block capacity. So like in the picture, there is actually like the block limit depicted today in a space of like two resources, like data and compute. In reality, there is more. But just like to like convey the idea. So the constraint we have today is kind of similar to the green line, where like the block gas limit is like, first you aggregate all the resources and then you impose a limit. The blue line is the safety limit for data, and the purple line is the safety limit for compute. So ideally, we would like to pack blocks so that we can utilize like basically all the space in the square. So in reality, like we cannot do this today. So basically the yellow area is like safe blocks that essentially we cannot build because the limits are like in a way too tight. Like the structure of limit does not allow us to go there. Yeah, so how can we improve from here? So first, we need to track the gas that is consumed by each resources. So if you assume that there is n resources that each opcode consumes, the reality is that most opcodes actually only consume compute. And there is maybe like 10 to 20% of opcodes that also consume other resources, but these are quite important. Yeah, so we meter all of these during execution, and then we define this new variable that we call gas meter in the block, that basically we take the max of gas consumed across resources. And then we can use this block's gas metering to like control the block capacity and also to update pricing. So essentially what we are doing at every block, we are updating the price just on the bottleneck resource. Yeah, one simple example is, yeah, like if you have data and compute, essentially like if one of them is at capacity, then you will increase the price. Otherwise, not. So essentially what this does is that, and both of them can be at capacity at the same time, right? So what this does essentially, it allows us to move from like this block limit model to this. And essentially we can be efficient, but while still respecting the safety limit for each resource. Yeah, this is only a first step. So essentially, in the simplest version of the proposal, we don't change price at all. So there is still like one single price for gas, and there is a minor change to the 1559 update rule. And this update is simple, like it's safe, and I would argue is valuable. Like there were like some simulation work being done where you can actually increase throughput by like 2x, or like in some extreme cases even 4x, without compromising too much, without compromising on safety. But it's still suboptimal. So like we are not pricing the resources right. Like if there is only one resource that is overutilized and all the others are slack, you are effectively like increase the gas price. So you increase the price for all resources. So we need a second step basically. And what this second step should do, basically, like we would like to approximate the market clearing price for each resource separately, right? So that essentially like each resource is priced optimally. And this is what the unified multidimensional pricing proposal is trying to do. I'll give a sketch here. So essentially, like what we want to do, like for multidimensional pricing, is like now the protocol is going to maintain k prices if there are k resources. Yeah, the cool thing is that actually, like we call unified because this can also include the blob market and the data market that today is something separate. So it's basically a unique framework that we can really like have this general framework where we price all resources in the same manner. Yeah, and then like the price for a resource is just update based on like supply demand imbalance of that resource only. And in order to do this, we also need to change we need to introduce a new transaction type. Yeah. So I guess it's like a little bit more involved on that side, but I think that's important because we still want to keep like decent UX. That's another constraint that we have in mind when designing this. Yeah, so essentially like there is going to be this new transaction type where like there is two main changes. One is we go from fee per gas to aggregate fee. So what does this mean? Like if you look at the fields that are related to the fee market in the EIP-1559 transaction type, basically there is the max priority fee per gas and the max fee per gas. So today, as a user, you don't specify your willingness to pay for the entire transaction. You specify the willingness to pay for each unit of gas. And then, I mean, the wallets already like kind of help with this, abstract this, but this is kind of a bit constraining when you try to do like multi-dimensional pricing. So the change here is just that in this new transaction type, then the user like just specifies like the max fee, the max total fee they want to pay, and then like the max priority fee they want to pay, which is also more intuitive, is how like potentially like many users already think about transactions today. And then the second change that you need to do is like how do you implement the gas limit for a transaction, not for a block. Here we're still like at the transaction level. So there is two options. One is like essentially you still meter like resources in different buckets, but like you map them to gas. So you keep one single gas limit over all resources. The second option is that actually the gas limit, if you have k resources, you specify k gas limit. Still, like the fee parameters is going to be unidimensional, but if you have 5 resources, you need to specify 5 gas limits. The wallets can also help with like kind of estimating this. And basically, like there is just a trade-off between UX and efficiency, or like let's say capital efficiency in this case. So if you do option one, arguably you have a better UX on paper, I say, because like you only have one parameter instead of five. Like let's say in the case of five markets, five resources, but essentially, like when you compute whether like an account has enough balance to like pay for the transaction, you need to like do it in the worst case. So you need to take the resource with the highest price and use the gas limit, even if your transaction may not really use that resource. So it's kind of very inefficient because you need to have like more in many cases more balance than you need. So option two, like if you have k resources, you need to add k-1 parameters, but it is more efficient because now like you can set the gas limit for each resource separately. If you're not planning to use any resource in that transaction, if there are some expensive resource you're not planning to use, you just put the gas limit to 0. Yeah. So I guess it's under debate which one of these model will go in, but both are feasible, and I argue that both provide like decent UX. Yeah. So maybe to summarize, like if we combine multi-dimensional metering and new transaction type, they give us like this endgame EIP-1559. We get to fully utilize the resource capacity of a block. We have efficient price updates for each resource, and we have no degradation in user experience. The cool thing is that, as I said before, we can unify like the fee markets across different resources, which today it's kind of a problem, like we've seen with the blob fee markets, and there is also some work from people in the room that like highlight the challenges. And so when we ship an improvement, it's an improvement to like all fee markets. And actually, like I just gave the sketch of the main ideas of the two proposals, but like there is much more detail, and like there is already a few improvements. Like in the unified one, there is like also reserve prices, and then it's easy to add new resources as long as we can meter them. Then we can add them to the framework. Yeah, for the next steps, like both of these are like kind of in the stage of EIPs being drafted. So one is the multi-dimensional gas metering. You can look up this practical proposal on ETH Research. And then the other one, unified pricing, yeah, also in draft stage. Yeah, and that's all I have. Thank you.
Just curious, if you've got multi-dimensional fees and you're holding the pace of block production constant, you've always got a knapsack packing problem, which is where the efficiencies are coming in. Is there anyone at Ethereum looking at variable time? Using time to adjust the comparative efficiency with which the various silos contribute to the pace of block production, so you can get rid of the knapsack packing problem completely.
So like I don't agree that you always have this knapsack packing problem, because like most of the blocks are not full. So like for the blocks that are not full, you can just greedily pack them. Like you don't need to optimize anything. When you do have, yeah, it's a little bit more complicated. I would say like we are not looking at like changing like slot times in that context specifically. Other people are looking at like changing slot times for other reasons, but yeah, not in this context.
Any other questions?
So what do you think are like the worst case scenarios from like a super adversarial point of view that could be enabled by this change? Like, are there any like weird resource lockouts or like things like that? How do you reason about the space of new behaviors that we're introducing?
Yeah. So it's actually, that's a very good question. And I think like once we put forth these two proposals, that's most of the discussion that is going to happen. Like actually for each of them, there is like some edge case scenarios. yeah, we looked into some of these. Also, we looked into how this plays out with like fossil and like the censorship resistant EIPs. Yeah, there is a bunch of cases considered in the EIPs. Maybe like.
Okay. Yeah. I'll stay tuned for that discussion. Thanks.
Oh, I just got a simple question. So obviously, it's quite obvious why this is quite useful, but have you quantified how much better it is than the current system and whether it's actually worth doing? Because obviously it takes like a lot of time to implement and everyone else around it, especially if you modify how the transaction looks.
Yeah. So we just have like some simulation and some backtests that Maria, like one of the authors of the multidimensional metering did. So like on average, I think she was finding that you can increase by 200%, like capacity, like basically the number of transactions you can include while keeping the same limits. But then we were also talking to Marek at Nethermind. He thinks that like in the cases where like the blocks are full, like or I don't remember exactly like which kind of extreme load cases he was considering. He says that this can go up to like 300-400%, but of course that's like a small fraction of blocks. But yeah.